Okay, so in this section, we're going to talk about another concept in integration called indefinite integrals, and we're going to compare indefinite integrals with definite integrals and work a few more examples of definite integral computations. All right, so we saw that the second part of the fundamental theorem of calculus is a way of evaluating the definite integral of a function. And that, of course, assumed that we can find an antiderivative of the function. Okay, so indefinite integrals and the net change theorem. Okay, so we introduce a notation for antiderivatives, review formulae for antiderivatives, use the formulae to evaluate definite integrals, and reformulate the second part of the fundamental theorem of calculus 2 so that we can solve some engineering and science problems. All right, so part 1 of the FTC says that if f is continuous, then the indefinite integral from a to x of f of t dt is an antiderivative of f. And part 2 says that we can evaluate the definite integral from a to b of f of x dx by evaluating the antiderivative of f from b to a. Okay, all right, so we've seen that. So we need a convenient notation for antiderivatives that makes them easy to work with. So due to the relation given by the FTC between antiderivatives and integrals, so the integral from f of x dx is traditionally used for an antiderivative of f and is called an indefinite integral. So right here, this is the symbol. The integral from f of x dx is equal to the antiderivative of f of x. And that means that the derivative of the antiderivative is just the function. All right. So for instance, we can write, basically what it's saying is that the indefinite integral, you don't have upper and lower bounds for the integral symbol. And you just take the antiderivative of the function in the integral. And so the antiderivative in this case of x squared is x cubed over 3 plus c, because when you take the derivative, you get back the argument. Okay, so that's all we're dealing with here. So definite integrals have upper and lower bounds. Indefinite integrals have no bounds. Okay, and so here's the connection. The definite integral is the evaluation of the indefinite integral from along the bounds of the definite integral. Okay, so we can go back to section 4.9 for a table of antidifferentiation formulae. So for instance, the indefinite integral of secant squared x dx is tan x plus c, because by the fundamental theorem of calculus, part 1, if we take the derivative of the tangent function plus c, we get back the argument to the indefinite integral, which is secant squared c. So, and so here's table 4.9 from section 4.9 again. For instance, the antiderivative of a to the x is a to the x over natural log of a plus c, because if you take the derivative of the right-hand side, you'll get back a to the x, and so forth. Okay, so we've done this. Table of indefinite integrals of some known functions. So for instance, the antiderivative of cosh x is sinh x. The antiderivative of sinh x is cosh x. The antiderivative of 1 over x squared plus 1 is inverse tan of x, and so forth. Okay, so section 4.9 revisited again. So you add a constant to a particular antiderivative to get the general antiderivative, and that's what we'll do here. Okay, so for instance, the evaluation of the indefinite integral 1 over x squared dx is the antiderivative of 1 over x squared, which is negative 1 over x, plus your integration constant. And of course, the understanding implicit in this solution is that we're only taking the integral from 0 to infinity or from negative infinity to 0, okay? If we're going to write it as a d and e. So 0 is not in the bounds for integration. Okay, so the antiderivatives. So it's now a piecewise defined function. Okay. Find the general indefinite integral for this function. So we just go term by term and take the antiderivative of each term. So here we split the integral using the properties of integrals right here. Okay, we split the integral and we kick out the constants that are involved in the integration. And so we just go term by term. So this would be the antiderivative of x to the fourth would be x to the fifth over 5 times 10. And then the antiderivative of secant squared x is just tan x. So minus 2 tan x. And then we have an integration constant. So this c value is the composite integration constant from evaluating these two. So it's a cumulative sum, right? And so after simplifying, here is your function, your antiderivative. And then you can always check by taking the derivative of this function, your answer, and seeing if you get back this function. Okay, so check the answer by differentiating it. All right. So evaluate cosine theta over sine squared theta. All right, so we can manipulate it into a familiar product of functions. So cosine theta over sine squared theta can be recast as you can see here, cosecant theta, cotangent theta, d theta. And we know the antiderivative of cosecant theta, cotangent theta is simply the negative of cosecant theta. And then we tack on or add on our integration constant, and we get this result. Okay, so we can do more complex functions. Right. Okay, so now we can go back to a problem we worked in the previous section, evaluate the definite integral from 0 to 3 of x cubed minus 6x dx. So using the fundamental theorem of calculus part 2, excuse me, we can take the antiderivative of each term in the polynomial. So the antiderivative of x cubed, of course, is x to the fourth over 4. The antiderivative of negative 6x is negative 6 times x squared over 2. And then we evaluate the antiderivative from 0 to 3, not being concerned about the integration constants. So we evaluate this polynomial right here at x equals 3, which is right here. And then we evaluate the polynomial at x equals 0, and we subtract the two quantities right here. And then we get, again, our solution, which we arduously found using sums of areas of rectangles. So you can see we reduced 4 pages of calculations down to a third of a page. All right. So find the definite integral from 0 to 2 of this function. All right, so we can do that here. We just go term by term taking antiderivatives. So this would be 2x to the fourth over 4 minus 6x squared over 2 plus 3 inverse tan x. Okay, and then we evaluate it from 0 to 2. And so that would equal to what? That would be 16.8 minus 12 plus 3 inverse tan of 2. Okay, and if we plug in 0, we'll get 0. So in terms of areas, okay, so the area under the curve from 0 to 2. So there you have it. Okay, so negative 4 plus 3 inverse tan. So this is the exact value of the integral. So take a look at the anti-differentiation of each term in the function. Then use the evaluate it from 0 to 2. And so doing so, okay, so use a calculator to get inverse tan of 2. So it's negative 0.6785. And, oh, they even graphed it. Here's the graph. All right, so this is actually from section 5.2. Okay. So that's why it's negative, because there's more negative region than positive region. Okay. So evaluate, let's do another definite integral example. So as I always suggested, replace radical notation with exponential notation, and then do the division. So after doing the division, the function is 2 plus 2 to the 1/2 minus t to the minus 2. And then you just take the antiderivative of each term in the polynomial, okay, to get the indefinite integral. So it turns out to be 2t plus t to the 3/2 over 3/2 minus t to the minus 1 over negative 1. Evaluate it from 1 to 9. Okay, This evaluation is basically called the net change theorem. Okay, so evaluate it from 1 to 9. First you plug in 9, get the quantity in parentheses, then you subtract off the result when you plug in 1, and then you get 32 4/9. Okay, so that's basically considered the net change theorem. So if f is continuous on a closed interval, yeah, so we've seen that. Okay, some applications. So f prime of x represents the rate of change of f of x with respect to x. So fb minus fa is the change in y when x changes from a to b. So y could be, for instance, the increase and decrease and increase again. Although y might change in both directions, f of b minus f of a represents the net change in y. Okay, so what it's saying is, yeah, the net change in y. Y could be changing in a positive sense and a negative sense from a to b, but the net change, the overall change in y, is still evaluated at the endpoints of the interval of integration. So that motivates the net change theorem. So the fundamental theorem of calculus part 2 says the integral of a rate of change is the net change. Okay. Okay. Although f prime of x may take on different values between a and b, the net change will be the antiderivative of f prime at b minus the antiderivative of f prime at a. Okay, so some examples, I guess. So if Vt is the volume of water in a reservoir at time t, its derivative, V prime of t, is the rate at which water flows into the reservoir at time t. So so this formula is the change in the amount of water in the reservoir between times t1 and t2. The volume at time t2 minus the volume at time t1. Okay, and expressed in terms of the rate of change of water flowing into the reservoir. Okay. Civil engineering problem there. Okay. So the concentration of product of a chemical reaction. Okay, so you know that the concentration changes with respect to time, and so the net change in the concentration will be the concentration at the final time minus the concentration at the initial time. And the way you can deduce that is if you know the rate of change, concentration with respect to time, then you just integrate it over the time interval to find the net change. Okay. The mass of a rod, similarly, okay, so we're going back to all those other problems. The rate of growth of population, okay, so all of these are coming back now. The C of X, the changing cost of production of a commodity, you just integrate the marginal cost from the initial production output to the final production output. Okay, so if an object moves along a straight line with position function st, then its velocity is the derivative of the position function, so integrate the velocity to get position over a time interval. That would be the net change of position or the displacement during the time period from t1 to t2. Okay, so calculate the distance the object travels during a time interval. We have to consider the intervals where v of t is greater than 0, the particle moves to the right, and v of t is less than 0, where the particle moves to the left. Okay, of course. So in both cases, the distance is computed by integrating the absolute value speed. Okay, so the total distance an object travels. Okay, so it's conceivable that an object travels this way. Okay, then it turns around and it travels this way. Then it turns around and travels this way. Okay, and then it zigzags back and forth like this. That could happen. But if you want to calculate the total distance traveled, you have to calculate the distance traveled along here, add it to the distance, add that to the distance traveled here, add this distance to the cumulative distance so far, and then add this distance. So that's why we take the absolute value of the velocity function. Okay, that would be the total distance. So it would be distance A plus distance B plus distance C plus distance D. That is, the absolute values of these 4 distances would culminate in the total distance traveled. Okay, so that's why we take the absolute value. It's the distance, not the displacement. The displacement, of course, could be some small number, whereas the distance would be a larger number. Okay. Okay, so displacement, of course, is the net change. It would be A1 minus A2 plus A3, okay? And we recalled from section 5.1 that the area under the velocity curve is the distance traveled. And so the displacement would be the positive displacements minus these areas under the curve, okay? But the total distance traveled would just be the sum of the absolute values of each of the displacements. So you can see the difference. The two quantities would be considered different. Distance versus displacement. So the acceleration of an object, of course, is the acceleration is the antiderivative of acceleration, of course, is velocity, because the derivative of velocity is acceleration. All right? And so particle moves, so in this example, okay, so so a particle moves along the line so that its velocity is given by this function. We've seen this before. Find the displacement of the particle during the time period from 1 to 4, okay, and then find the distance traveled. Okay, so the displacement will just be the evaluation of, all right, so the displacement would be the evaluation of the integral from 1 to 4 of v of t. That's your displacement. And we just use net change theorem to find displacement. The distance traveled would be the absolute value of the velocity function, the definite integral of the absolute value. Okay, so that's the distinction. Okay. All right, so let's see how they solved it. Okay, so here's the displacement. They took the antiderivative of t squared minus t minus 6, which of course is t cubed over 3, minus t squared over 2, minus 6t, evaluated from 4 to 1. So your displacement is negative 9/2. So the particle moved 4.5 meters to the left, s of 4 minus s of 1. And this is the net change theorem. Now, as far as the distance traveled during all of this, we have to take the absolute value of the function. Okay, so v of t is equal to t squared minus t minus 6, which factored is t minus 3 times t plus 2. So using the table of signs, which I won't go into, you can deduce that v of t is less than 0 from 1 to 3, and v of t is greater than 0 from 3 to 4. Okay, so you would have to split the integral now. So by definition of absolute value, from 1 to 3, we replace the negative of the velocity component. Okay, using the definition of absolute value, which I've said dozens of times during the semester, and then we evaluate the function from 3 to 4. So from 1 to 3, the function is defined as negative t squared plus t plus 6, and then from 3 to 4, it's defined as t squared minus t minus 6. Okay, and then we just use net change theorem for this. Okay, so evaluate the two integrals, and we get 10.17 meters. So that's this total distance traveled back and forth. Okay, so I'm hoping you see the distinction between the two quantities. Figure shows power consumption in San Francisco for a day in September. P is measured in megawatts. T is measured in hours starting at midnight. Estimate the energy used on that day. All right, so the energy used is probably the area under the curve. This is an electrical engineering problem. So the power is the rate of change of energy, so power is equal to the derivative of energy. So the energy consumed would be the area under the curve from 0 to 24 of the power function. And so the power function is equal to the derivative of the energy function. And so by the net change theorem, this would just be the energy at 24 minus the energy at 0. So that's the total amount of energy used in the day. So you just read these 2 points from the graph. We approximate the value of the integral using the midpoint rule with 12 subintervals in delta t as follows. Okay. So, so they're using the midpoint rule, good grief. All right. Well, anyway, so 12 intervals, the midpoint, so part 1, 3, 5, 23 times delta t, which is 2, because they're splitting a 24 length from 0 to 24 into the width would be 2, so the area under the curve So the energy used in watts was approximately 15,840 megawatts. So they used the midpoint rule from that previous graph. Used for energy. How do we know what units used for energy? Well, the integral is defined as the limit of sums in terms of the form P at sample point times delta T. Now P at sample point is measured in megawatts and delta T is measured in hours, so their product is measured in megawatt hours. The same is true for the limit, so megawatt hours is energy. In general, the unit of measurement for is the product of the unit for f of x and the unit of x. Okay. All right. So this concludes section 5.4. We basically just used the net change theorem, and we evaluated definite and indefinite integrals. And needless to say, there will be quite a few web-assigned problems in this topic. And also quite a few test questions on this topic. This topic will be very important as you go into Calculus 2. So if you're going on to Calculus 2, your first day of class will probably start off with problems like this. So it is extremely important that you become proficient in this subject matter and understand it thoroughly. If you have any reservations, send me an email, request hints, or visit me during my office hour. All right? Okay, so that's it for section 5.4.